So when we developed DPX, really what we were looking at was a range of pipelines where we found that the existing technology wasn't suitable. Our volume balance systems that we had developed were highly capable in some applications, in many applications, but there are locations with short stub lines, short laterals, where you don't have the instrumentation that you need to be able to perform an effective volume balance. You have locations that don't have sufficient data coverage. You might have outages with your communications, so you can't rely on getting that data effectively to be able to process it. And you might have high consequence areas, locations like river crossings, that it's not enough to know that there is a leak on the pipeline. You need to know, is this leak at this river crossing? Because that drastically changes the way that you respond to that leak. And that's where we started to develop DPX as a solution to fill in those gaps in traditional leak detection systems. So traditionally in our volume balance applications, we use instruments and meters that are already on the pipeline. So that would be Coriolis meters, flow meters, maybe turbine meters that customers would already have installed in their pipelines, where they're already gathering the data and sending that information to their existing database. We would tie into that and we would extract that information. We would make expert predictions about that, about whether there is the presence of a leak on the line, and we would return those predictions to the customers. DPX is really a first for us because we're putting out our own hardware into the field. We're putting out these edge computing kits. So it's going to be a small skid that sits beside a critical point on the pipeline. It's got a solar panel on it. It's got an edge device inside of a hazardous rated panel. We're going to have a data acquisition system inside of it as well as a cell modem, which could be upgraded to a satellite modem if need be for the communications. And then we're going to be tied in directly to the pipeline with a dynamic pressure sensor, which is a piezoelectric sensor that's sampling at an extremely high frequency, typically about 10,000 hertz, that we're going to be collecting dynamic pressure data straight from the pipeline and processing that on-site ourselves. So once we're connected to the pipeline, we're using the dynamic pressure of the flow to be able to make predictions about whether there's a leak or not. Our dynamic pressure sensor is collecting data at 10,000 hertz from the pipeline, which is a very large volume of data, and we're processing that on site. We've got a machine learning model which runs on our edge computer, which is going to study that data received from the pipeline and predict whether or not there's a leak either that has occurred or is occurring in the vicinity, about 1 or 2 miles in either direction from the sensor which is connected to the pipeline. Once it makes that prediction in the edge computer, it'll send that by cell modem to our own cloud-based database, where we are able to access that afterwards to display the results in our own HMI, or we can send that information to the customers so that they can get it in front of their operators to be able to see, is there a leak? How confident is our system in the presence of that leak? And other signals that would be associated with that as well, like background noise trends on the pipeline and so on. When people think about pressure-based leak detection systems, there's a couple methods that they would already be familiar with. The most common is going to be set point-based, where you would be looking to see whether the pressure on the line drops below a particular set point or predetermined threshold. And the second method would be a negative pressure wave-based system, where you're looking for the shock that's released when a leak occurs that travels along the pipeline to reach an existing pressure sensor. And both of those methods use gauge pressure or absolute pressure, which would be like your standard pressure transmitters. DPX is really different from those systems. It measures the dynamic pressure of the system. So that's going to be the component of the pressure which is associated with the velocity of the flow. So when the flow is moving, it creates this dynamic pressure signal. And it's not what you would normally think about when you hear a pressure transmitter. What we see is that both of those previous methods that use pressure to try to detect the presence of leaks, they have some challenges that I think many operators are familiar with. A set point based approach, the big challenge there is where are you putting your set points? So when the pressure drops below a certain point, the expectation is that the system would alarm because it thinks that there's going to be a leak there. The problem is that changing conditions on the pipeline, transient conditions, can change what the baseline level of the pressure in the pipeline should be, and thus where your set point should be at the same point. And historically, these kinds of set point or threshold-based methods for pressure have resulted in a lot of false alarms and a lot of nuisance alarms that operators need to deal with. Negative pressure wave is actually a really interesting method. It's looking for that shock that's released when a leak occurs on the pipeline. It's like a one-time event that travels or ripples through the pipeline. And if you've got a very finely tuned pressure transmitter, you can pick up on that negative pressure wave when it reaches it. And not only can you say there was a leak, but you can say how long did it take to reach me based on time of flight calculations. And I think a lot of people are drawn to it for that reason, because it can, to some sense, localize where the leak would have occurred on the pipeline. The downside, though, of negative pressure waves is that it's a one-time event. So if you miss that event when it happens for whatever reason, maybe you've got operations on the pipeline at the same time, maybe there's transient conditions, maybe the leak occurred at an earlier point when it was shut in, maybe, any number of things, communication outage that could result in you not registering that leak when it first occurs with a negative pressure wave based system. If you don't detect it that one time, you'll never be able to find it with that approach, because it's this one-time event that goes through the pipeline. So I think that people are maybe familiar with these kinds of pressure-based approaches, but and maybe have moved on from them in many cases to flow balance as kind of the most robust overall solution for leak detection. DPX, it's very different from those sorts of approaches. Not only is it using the dynamic pressure and machine learning to be able to pick out the leak from the background intelligently so that you don't run into those kinds of thresholding issues. The other big advantage that you see with it is when the leak is occurring, it's continuing to create the noise in the pipeline. We're acting not necessarily as a pressure meter, but as a microphone or as a hydrophone inside the pipeline, listening for the sound of the leak that would be occurring in the vicinity, both upstream and downstream from the point of insertion into the pipeline. When a leak occurs, it creates noise that's channeled down the pipeline, and we're able to pick that up against the background noise. So the system can be installed, it can pick up a leak. When it happens, it can continue to pick it up as it continues to leak afterwards. The system will remain alarming, or the system could even be installed after a leak has already occurred, and we would be able to pick up that leak against the existing background noise of the pipeline. And as the machine learning model learns what the typical conditions of the pipeline are like, then the leak detection that it can provide just gets better and better. So we developed DPX for applications where we saw there was no good solution right now. And there's three in particular that I would mention where DPX is a really good fit for the challenges that we see that operators face. So first of all, it's going to be for short stub lines, short laterals, short segments of pipe that don't have existing flow measurement on it for one reason or another. So you can't perform an effective volume balance or mass balance. The second application that we would look at is going to be for custody transfer lines, where a given operator only has access to one end of the pipeline. So they don't even have the capability to perform a volume balance on what's happening at the other side. And the third application is really for high consequence areas, river crossings, those kinds of very sensitive locations that need immediate call out. Is there a leak? Did it happen near this really important location? Or is it somewhere else in the pipeline, which changes your response dramatically? We see that there's a lot of short segments of piping. They might be 1 mile, 2 mile in length, usually between maybe like a facility and a gathering node, or between a header and a well site. We see a lot of these little short stub lines and laterals where to perform a really accurate volume balance, you would need 2 flow meters on that line. You would need one at the inlet and you would need one at the outlet. And the challenge with that is it's very expensive. Flow meters are very expensive, and a lot of times it's cost prohibitive to be able to have turbine meters, let alone very high quality precision instruments like Coriolis meters at both the inlet and the outlet of each one of these. And it's a ton of data to manage as well in those cases. So the advantage of DPX here is if you don't have existing instrumentation, if you don't have the existing data architecture for it, if you aren't set up with your SCADA system or anything else to be able to process that data, DPX is a really hands-off standalone system that can go out, it can tie into the pipeline, and it can listen over the length of that entire pipeline. Is there a leak that develops at any point? It doesn't need flow measurements. It doesn't need any other existing instrumentation that would be available. It can just listen to that one segment and say, when is there a leak that develops on this? DPX has been in development for a number of years, building the algorithms and the data collection methods to be able to accurately get the information from the pipeline, from the dynamic pressure sensor, and process that with our machine learning models that have been developed to really provide operators with confidence about the predictions that it makes. We have a rigorous MLOps methodology to be able to train and deploy new models to the pipeline as the conditions on the pipeline change, to make sure that we're keeping up with changing flow conditions, changing background noise, and what we learn about the pipeline. The predictions that we make all have confidence scores that are associated with them, so that operators have knowledge about how reliable is this prediction that's being made and how sure is the system about this. Any alarms result in an auditable data log where information is going to be saved to external drives for later analysis. And we always have a trail of how did the model come to these conclusions so that we can interrogate it afterwards. The system has performed extremely well in early development and early trials that we've used it on over the last number of years. Generally, we're able to achieve 100% recall with our aggregation method, which is essentially going to be when there's a leak, the system is always going to be in alarm, which is the most important criteria that we generally look for. At this point, we have 3 to 4 operators that are using DPX on their pipelines to listen for leaks and provide them with that actionable intelligence to be able to respond appropriately. We've developed DPX for a number of different applications, field conditions, environments that it might be deployed to. It's a very robust, rugged, and flexible design that can be adapted to your needs. The enclosure and all of the devices are rated for Class 1 Div 2 operations. It's suitable for minus 40 degrees, so it's good for winter deployments or for summer. It can be tied into your site power, or it can be powered with its own self-sufficient power system with the solar panel and the standby power with batteries on the device. It can be mounted in our A-frame panel, or it can be mounted at your own facilities. So it's really tailored to your layout, your needs, your application, and we would love to have the opportunity to sit with you and show you how the system works and how it can be deployed for your particular needs.